So we have studied that QFT is a function from geometrically enriched properties to vector algebra. Second, we studied that when vector algebra is replaced by modules over tropical ring, we get classical field theory. And we also studied that there is a Feynman proposal and Feynman proposal is just to do functional integral. And what we have also studied is that deformations of QFT correspond to local observables. In the way that deformation of functor is integral over p over x, deformation of functor applied to x. Sorry, I'll write it in bigger letters. So x is a manifold. Okay, I'll write it like this. So you need to study local observable and you need to integrate over position of the local observable over x. And what else have we studied? I want it to be written very clearly, so I write in big letters. Right. So-called ultraviolet divergence are problems in writing down. Second variation of f of x as integral over p1, p2 that belong to x cross x of f op1, op2 because of divergences potential divergences as diagonal. So these are the main things that we studied about quantum field theory. Now, what I'll do today, I'll try to consider this Feynman proposal. And the topic of today's talk would be, okay, so I just want to show what I wrote here. Ups and downs of Feynman proposal. So mostly I will discuss ups of Feynman proposal. So what I will do, I will remind Feynman proposal for the simplest model. Maps of an interval to a line in which action is just integral of the square norm of velocity dt. Second, I will describe so-called Feynman quantization. I will study basic observables. Point number 3. Generalization of Feynman proposal for a model where this interval is mapped to a circle of length L. And here, as a point 4, I will do 2 treatments.
Camera loss focus.
Lost focus. So, is focus back?
Yes.
So there will be 2 treatments of this interval to S1 model. One would be called punctorial, and another would be called Feynman. And then we check that there will be a strange conjecture. That these treatments give the same answer. And yes, they do. And this is example of how mathematical physicists predict mathematical conjectures. It will be prediction of Poisson formula. And if we will have time, we will start what is wrong with Feynman's proposal for second deformation of the function. I am not sure that we will have time for it, but it is a very important point that I am going to start today. So this is the plan for today's talk. Now some notations. How physicists understand maps. If you have a map from an interval to R, then coordinates on maps are pullbacks of x over this axis coordinate on R. So they belong to functions of the interval. And physicists write gamma star of x as x of t. I would study action given by m over 2 dx over dt squared dt from 0 to t. And I would like to consider integral over gammas with the condition that x of 0 is x0, x of t is xt, and here I have e to the I s over h. And what we discussed last time is that this integral is some function that may depend on what? That may depend on h bar, m, t times exponential I over h, m capital, xt minus x0 squared over 2t. What was important is that this c was independent of x0, xt. I will briefly remind that in order to do it, we said that x of t could be decomposed into x classical, that depends on t, and parametrically on initial and final conditions, plus psi of t, with the conditions that psi at 0 was equal to psi at t capital was equal to 0. And x classical was of the form x0 plus t over t capital xt minus x0. I plug this here, and here is the value of the action on the classical trajectory. And here I have these xi terms that factorize in this integral. And the integral over this xi term, infinite dimensional integral, is this. I have two choices. I can either consider this as infinite dimensional ill-defined determinant, or I have an opposite choice, and opposite choice is just to say, look, this is an answer, let us plug it in, factorization condition, and define, and that's how we are getting this C of t. We can do both. However, so in order to go faster, we take the second approach. Let us assume that things go right. So we can just compute this C out of this expression. You see, today I am here after the long break, so I'll just repeat the basic steps. How can we compute this C? Functoriality. Conditions say the following. C T1 times C T2. And here I have integral over d x tilde. So x0, x tilde, x t1 plus t2. Okay, maybe I will call it t1. So then I'm integrating over x t1. Of what? Let me call this term. You see, m, h, 2t. Let me call it t tilde. To simplify notation. E h divided by m. Okay, maybe I even want to pretend this h, to let you have a trace of this h. So I have integral over this, and what I have here, exponential of I over h. x0 minus xt1 squared divided by t1 tilde I over h xt1 minus xt1 plus t2 squared divided by t2 tilde. So I put this sum in the exponent. And I want it to be equal to c of t1 plus t2. And here I want to have an exponent of I over h. Okay, so there is 2 here, and there is 2 here.
Excuse me, don't we need to write C function from h bar met in integral?
This is a multiplier. So here we have that
Oh, okay. I see. Thank you.
t1 plus t2 tilde over 2. So this is the very important check. It is so important that today I will do it on the board. Okay? I just want to say that what we have here is a Gaussian integral in xt1. So we would be able to perform it. So what is that important about this Gaussian integral? Is that, first of all, we have this thing in exponent. Let me remind you that there is the following formula. I can even put I here. So this is 1 over square root of a. And what do I have here? I have here exponent of a of I, and here I have b squared over a. And here is some numerical thing that I don't want to carry. Something with i's and pi's. It's not that important.
And it's probably b squared over 4a.
Over 4a, of course. So it's better for me to put here 2. And if I put here 2, then it will be b squared over 2a. I think it will be like that. Well, and we can also rewrite this as e to the I, and here is the s critical. Or let me call it ax critical square over 2 plus b x critical. So what is x critical? X critical is the minimum of this function. So let us check that it is true. I'm doing this example because it is a basic example of how critical values appear. So x critical is, of course, solution to equation a x critical plus b equals to 0. So x critical is minus b over a. And if I plug this x critical here, I will get ax critical squared over 2 plus b x critical equals to a over 2 b over a squared minus b times or plus b times minus b over a. And this is minus. Here I have an important minus. B squared over 2a.
Maybe we must write minus at first exponent in answer. I remember that when we count Gaussian integral, we must to change
Yes.
second. Yes.
Yes. So here the answer is like this, and here the answer is like this. Thank you. So computations are in front of you. So you may even check this side. So it is an important lemma. So now let us apply this lemma to our problem.
Excuse me, I speak one thing in Russia. В третьей формуле минус не нужен. Вот третье равенство с экспонентой, там уже лишний минус.
Thank you. Thank you for correcting me. Now, let us apply to this particular example. So what is x critical? It is solution to the following equation. X naught minus xt1 divided by t1 tilde plus xt1 minus xt1 plus t2 divided by t2 tilde So it is the derivative that I have here. But I also have so what I wrote here. I took the derivative and I want it to be equal to 0. Derivative here and derivative here. Derivative in xt1. Now I may compute something out of it. I may
The
compute.
first sign is wrong.
I think there must be minus. Yes.
Yes, thank you. So now let us solve this equation. xt1, here I have 1 over t1 tilde plus 1 over t2 tilde equals what? Equals, so now to take things to the right. So this is the formula for xt2 critical, xt1 critical. So of course we will solve it right now. But after we will solve it, we will try to follow its meaning. xt1 critical, t1 tilde, t2 tilde, t1 tilde plus t2 tilde equals t1 xt1 plus t2 plus t2 tilde x0, and here I have this t1 tilde t2 tilde, and I may cancel it. Okay. So x critical is t1 tilde plus t2 tilde, and here I have t1 tilde xt1 plus t2 plus t2 tilde x0. Okay, I made the computation, but after I made the computation, I might look at the meaning of x critical. So here I have x0, here I have xt1 plus t2, and here I have times. Zero, t1 plus t2, t1. Here I have x0. Here I have xt1 plus t2. Now, where do I think x critical is?
At line which connects 0 and t.
That x critical is exactly here. So let me check it for particular examples. That when t1 equals t2, then x critical should be semi-sum. If they are equal, then x critical is, as you can see from the formula, equal t is 1/2 x0 plus x t1 plus t2. Now, what happens if t1 and t2 are different? Let me do it as follows. Let me draw equation for this line and check that its value at t1 is x critical. So this line is x0 plus t1 plus t2, and here I have xt2 plus t1 minus x0, and here I put t. So let me call it critical line of t. It's a critical line. Now let me check its value for t equals t2. It would be x0, and here I will have plus x t1 plus t2 minus x0, and here I have t2. And here I have this t1 plus t2. So I can put tildes here. No, I don't want to put tildes. So what would be if I plug t2? The things go right with denominator. And it is easy to see that if I simplify this expression, I will get t1 plus t2. Here I have x0, t1 plus t2, plus x t1 plus t2 times t2 minus x0 t2. Then this term cancels this term. So did I get it right? Ah, wrong. I should have t1 here. So this term cancels, not this term. It cancels this term. So I'm getting x0 times t2. I have it. And here I have x t1 plus t2 times, yes, and of course, here I need to have a t1. Yes, lemma proved. I managed to make this computation in front of you. So it is the meaning of this exponent. You see, I don't like doing computation, but when computations are that simple and that important, I will do it in front of you. Now, I have to work out this 1 over square root of a. What will this mean? So A is something that was in front of x squared. So we had the following thing. We had x t1 squared, and we had 1 over t1 in front of it, 2t1, plus 1 over 2 t2 in front of it, plus other terms. We had exponent of this. So 1 over, so it means that A was 1 over t1 plus 1 over t2. Good. It means, so we know that this is t1 plus t2, and here I have t1 plus times t2. Now, square root of A is square root of t1 plus t2, square root of t1 times square root of t2. So it means that in prefactor, I am getting that 1 over square root of A is square root of t1 times square root of t2 times this. And then factoriality assumes that c of t1, c of t2, and then this integral times square root of t1, square root of t2. And here I have square root of t1 plus t2. Due to factoriality. Conjecture. T1 plus t2. So now the question is, could we solve this equation? And the answer is yes, we can. Let's equal it F, factoriality equation. So F may be solved by C of t equals 1 over square root of t. And here I have a freedom. And freedom is exponential. So I plug. So how do I know that it is the answer? I do it like this. I consider C of t, that is 1 over square root of t times C tilde of t. And I plug it here. And I get a condition that c tilde of t1, and here I have c tilde of t2 equals c tilde of t1 plus t. So for c tilde, I have the exponential law. So that's how I get that c tilde equals exponential. And here what I would like to call it, maybe I. It's a definition. I E naught. Okay, so that's how I do it.
I think in process of computation we lost h bar because we don't put it in t.
Yes. So how to restore H bar?
Multiply t to h bar or h bar or 1, короче, h bar минус 1.
Okay, so how do we, so here, where it comes?
We just use dimensional analysis. That's how we restore
You see,
H bar.
I will do it simpler, without dimensional analysis. I have the following: x0 minus xt squared over 2t h bar. So h bar comes together with t. Okay. And I also have a mass here. So if I restore things, I will see that there is an H bar standing. So C of t actually equals 1 over square root of what? Here I have t, here I have H bar, and here I have m. Okay? So after all this computation, I got the final result. Final result. Probably with some I in front. So it's a very remarkable formula. Now, I have a feeling that I'm coming to a break. And it's not bad to have a break. Yes. Let me ask questions and let me go for a break. Are there any questions so far?
Well, if we want to keep track of this h, I think in the prefactor it should be, we got it wrong.
So
Because it's, we're supposed to replace t with t over h, not with t multiplied by h.
okay, so how can we get it?
No, what we did before was correct. We just we have to introduce this t tilde, that is t over h. Oh, or rather, t tilde is t multiplied by h, and then t is t tilde over h. So here, h in the prefactor, it should be next to m.
However, here it is here. So from dimensional
Yes, but
analysis,
that's because it's actually energy times t over h.
okay. So now let's try to see where we got it wrong. So Kim says that we should have things like this, right?
Yeah, but this is just a question of dimensional analysis. We just
Okay, but now let us suppose that we do not have dimensional analysis. How to restore proper power of h from pure mathematics?
well, in the original formula, we do what you wanted to do originally, and replace t with t tilde that absorbs both m and h,
Yes.
and then we restore it.
So you say that it should be like t tilde.
Right, and there it should be
Tilde.
exponent of energy times t tilde.
Okay, and t tilde was, but t tilde was of course t times h over m. So then we work in terms of t tilde. So I don't understand how we can separate this t, m, and h bar are coming into t tilde. Okay, so we will see it and check it after the break. Okay. So I still think that when I'm doing the Gaussians, I have the combination T, M, and H bar, so they're coming together. So that's why I think that here I should have T times H over M. And I'm not afraid of the fact that, as you say, it has a dimension. But let us have a break, okay?
I think functionality condition can't check the dimension, capital dimension of this formula, because there is two exponent at right hand side of equation and same exponent. Let's say speak in Russian. В общем, я пытаюсь сказать, что мне кажется, что общая размерность вот этого выражения она не может быть функциональностью отслежена. Потому что мы все это делаем как бы с точностью до константы какой-то, которая может быть размерной. Ну, насколько мне кажется пока что.
No, of course we can't track the overall dimension because our punctoriality condition is nonlinear. It has a multiple. It is a multiplication of 2 factors equal to 1 factor. So and we have integration. So the dimension of this C should be 1 over the square root of x. Well, 1 over the square root of length. And I retract my objection to the formula. It was correct. Yeah. Sorry, it's something got over me. This way is the right one.
Okay, good. So now we will. So it's now that we will do 10 minutes break. After we spend some time and some computational resources on deriving this formula, let us give another check that this formula is actually quantum mechanics. So to do this, let me make another computation. Let me call this formula K of xt, x naught, and also t. And I'd like to have m and h bar as parameters. And let me do the following computation. What would happen if I take the second derivative of k with respect to x, t? It's not an easy thing to do. That's why I will go to this simpler example. So let me compute what is this. So first I take one derivative. And then another. So when I compute derivative, I am getting here, so probably I'd like to divide by 2. It is ax, and here I have the same exponential. Then I can take derivative again. And what would I get? I am getting a e to the a x squared over 2. When I differentiate here, plus I get, when I differentiate here, a squared x squared e to the a x squared over 2. So altogether, I'm getting what? Without any simplifications, I'm getting a plus a square x square e to the a x square over 2.
Sounds good.
So you may ask, why do I need this formula? In a moment, you will see why do I need this formula. I need this formula because then I would like to compute another thing. D over dt of the same expression. One, okay, let me do it in the simplified way first. X squared over t tilde. Okay, I'll write it. I will stand up and write the following formula. Interestingly enough, I will have two terms again. First term would happen if I differentiate here, and second term would happen if I differentiate here. When I differentiate this term, I will get 1/2 1 over t tilde. Total sign would be minus sign. And the same function. Then I may also differentiate here. And I will get so how can I differentiate here? I differentiate exponent. I will get I x squared over t tilde. And then I differentiate t tilde. So I get minus 1 over t tilde. And here I have this exponent. Now let me try to compare this formula with this formula. Sorry, you see, to be more precise, I want to put this thing here, and when I differentiate, I will get this. Okay, great. Let me massage this formula a little bit. I'm taking this thing out. And here I have minus 1 over half, 1 over 2 tilde, minus I x squared Now let us see. After this long and hard computation, this thing and this thing are actually the same. If I say that A is 1 over T tilde. So what would happen with this formula? Actually, A is I over T tilde. So what I have here, I have term here and term here. So if I plug it here, I will get I over T tilde. If I plug it here, I will get minus 1 over T tilde squared x squared. You may see that up to the coefficient 1/2 and I, it is the same formula. Wow. So what I actually proved is if I put everything correctly, this thing is known as Schrödinger equation. You see, here I have one I, here I have I squared. And computations are just on board. So what I have proved? I have proved the following. That K is actually the exponential of, so if I try to see what does it mean, of T divided by H. And here I have Hamiltonian for H equals IH d over dx squared 1 over 2m. So in this way, I proved that I'm dealing with factorial quantum mechanics. So in this way, in this formula, factorial approach and Feynman approach gave the same answer. Now, if I identify P equals IH d over dx, then H looks like P squared over 2m. That was the Hamiltonian of classical mechanics. And this way, replacing P in classical physics by this differential operator is called quantization. In particular, commutator of P and X is I over H. The Poissonian bracket of P and X was what? Poissonian bracket in Hamiltonian mechanics. So what people were calling quantization many years ago was the following procedure. Take classical Hamiltonian, replace P by IH d over dx, get a differential operator, and study this. Now, I would like to emphasize an important point here. And this important point is that here we do have H bar. Because of this particular system, people thought that quantization is putting H bar However, from the functorial point of view, this putting H bar is just a particular example of quantum system. It's not fundamental. So, whenever people say that quantization is about putting H bar, you should consider these books as outdated. You could not replace a concept by an example. Yes, this example worked well in the world of real physics, in many cases. But you cannot replace one by another. In particular, when we will later come to the quantization of the spin, not quantization, to the quantum system of the spin, you would see no H bar there. Or you might say H bar equals to 1. So then what would this mean? And we will discuss it later in much more detail in our course. Okay. So let me see how much time do I have. Okay, I do not have a lot of time, so I will continue talking about it next time. Let me make just one conceptual remark. And this conceptual remark is the following. Let me go back to functorial picture. Suppose that X, or from which we are taking, so now X is a source. Is not an interval, but a circle. Circle has a length t, but it has no boundary. So, I'm sorry. Алло? 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 So, this circle has no boundary. So this is a function of t. So to write it like this, it's a smooth function on R plus. T is a coordinate on R plus. Well, then I may ask the following question. What is it? Functoriality means that circle could be cut and become an interval. So that's why f for the circle is trace of f for an interval. Now we know okay, so I'm erasing these nice formulas with a pity. Now we know that f for the interval is e to the th, p capital H. That's why f for a circle should be trace e to the th. Good. Now the question is, could we apply it? In our example? So in our example, f associated to the point is the space of smooth functions on R. Story is this.
Is that a point of the interval or of the circle?
At the moment, it's a point.
Well, I mean,
Boundary.
shouldn't we at some point have smooth functions on the circle and not on R?
No. Because this R is not metric. This R.
The target is still the line.
Yes.
All right.
Now, let us see. So this is Hamiltonian. How to compute the trace? Let us compute the eigenfunctions of H. E to the ikx. Sorry, I forgot 1/2m. I call them psi-k. It's traditional notation of physics.
Excuse me, camera lose focus.
1 second. Thank you. H applied to psi-k is k squared over 2m psi-k. So now, what I'm going to do? I'm going to compute the trace. Trace of e to the th is trace of e to the t. So it is what it could be. It's an integral over k. And here I have I t over h. Here I made a mistake. H squared. H squared k squared over 2m. Well, very good. I'm happy. I'm happy because I have an exponential. And I can compute this integral. So up to the factor of pi and I, what do I have? I have integral over dk e to the I t times h divided over m. So this was the combination that we used to have. And here we have k squared over 2. So the question is, can we compute such an integral? Yes, this integral is perfectly convergent. And this perfectly convergent integral is what? 1 over square root of this t times h over m. Okay, so we already computed something. Not that bad. And we did it in factoriality approach to quantum mechanics. Computed. Now, let us see what would functional integral tell us. But maybe I would like to postpone it for the next talk. That will be tomorrow. And you see, let me tell you what I will talk about next time. What if target would be a circle? Then psi k would be I k over LH, where K would be integers. Okay, 2 pi K over LX. Then everything would be very similar with one distinction. Trace would be sum. And probably you know what does it mean. Have you ever encountered such a sum? So Maxim, have you ever encountered such a sum?
Maybe, but I can't remember. How?
Tim, maybe you met such a sum before.
I think it's the theta function.
Exactly. This is theta function of period matrix that is 2 pi L square 1 over M. Okay, people write the differences. It's theta function of 0 and 2 pi K L, sorry, 2 pi L square 1 over 2M and probably I. It's an interesting mathematical object.
Proof of that is Fourier series, or how I can prove it?
So here I'd like to remind you that theta function in mathematics is defined as the sum over K I don't remember if they put I. So this is the definition of this famous theta function. And here we have this theta function of 0.
Okay.
And I want to tell you that it is something interesting. And tomorrow, without hurrying up, we would try to reproduce the same answer from Feynman integral. Because you see, the topic of my talk of my talks today and tomorrow is ups and downs of Feynman integral. And today I'm speaking about ups. And tomorrow I'll speak about ups, and then later I'll speak about downs. Okay? So now I have time for questions. Are there any questions or comments or remarks?
Well, so in this last example where the target was a circle, the source was still a circle. So it was.
Yes.
Mm-hmm.
So in the last example, Tim, you got it right. The source was a circle, target was a circle, and you can imagine trajectories that are winding around the target. And they would play a role here. And then you may think that this discrete number is exactly the winding number, and you would be wrong. And that's interesting. Okay? So I am leaving you with this puzzle.